We talked about regression, correct? We spoke about target variable, which is continuous in regression. We spoke about supervised approach. Supervised learning, correct? What else we talked about? We spoke about curve fitting. Shaina, give me some keywords.
It's a least square method.
We spoke about least square. Basically, we spoke about error. In error, we spoke about RMSE and R square. Correct? But R square we will be studying in detail today. RMSE we went through in detail. Correct?
Yes, sir.
So for the model to be better, RMSE should be lower or higher?
It should be lower.
RMSE should be as
Lower.
low
as possible.
Low as possible. Correct? What about R square?
Opposite.
Yes, Shaina?
The opposite.
It is opposite. It should be as high as possible. We spoke about train test split, correct? We spoke about train test split. The reason why we spoke about train test split is because whatever the data you receive, the historical data, you need to have some data as proxy for tomorrow. You need to have some data as proxy for tomorrow, which is unseen, basically unseen. And you use train data to train your model, and you use this data set to test your model on error. Correct? What is the preferred ratio for train test? What is the preferred ratio?
Around 75%.
It is, I could say 70-30 or 80-20. Okay. Is it done systematically or randomly? Is the splitting done systematically or randomly? Do I take like first 10 rows and then keep balance 8 rows for testing, or randomly I select the rows?
This we select randomly, sir.
It's randomly. Okay. Plus, we spoke about correlation versus
Regression.
regression, correct? Correlation is basically a
Value.
Whereas regression is an equation. You're hypothesizing a causation. Correct? And throughout the session, we stressed on minimizing RMSE. Correct? Minimizing RMSE. Basically, we have your explanatory variable, you have your target variable, and you have your predicted variable, correct? Where you find your error. How is error calculated?
Actual minus predicted.
Actual minus predicted. Once you have your error, you calculate your aggregate error, correct? That is nothing but RMSE. And we did Excel activity where we used solver to find my beta 0 and beta 1 values, correct? In solver, we ask the model to find out these values such that my error is minimum, and accordingly the solver solved and found these values, and I got my adjacent predicted values, correct? We spoke about the basic line equation y equal to beta 0 plus beta 1 x, correct? And if you plot a regression line
It is linear.
considering only one variable, this basically is your
One.
beta 0, correct?
Beta.
This is your intercept.
Yeah. Yes. Intercept.
And the
Slope.
angle is nothing but your beta 1. Are you guys with me?
Yes, sir.
Yes.
So you guys understood how a basic Excel, how a basic solver function in Excel solves this equation and gives you out the optimum value of predicted values, whereas you're with lowest error, correct? Now, any idea how does a computer calculates beta 0 and beta 1 values?
Using the values which we pass, that is x and y.
So basically, it has something to do with your calculus. Okay. In calculus, basically what you need to do is, for the equation y equal to beta 0 plus beta 1 x, you need to find betas, this beta 0 and beta 1, such that your error is minimum, correct? Let's say we have a mathematical curve, something like this. This is your x and this is your y. Okay. This is 0, 1, 2, 3, 4, 5, 2, 3, 4, 5. Okay. Now, let's say that we have this mathematical curve. Okay. Now, what is the minimum value of y? It is somewhere around
2 and
2,
3.
right? Y equal to 2. Are you guys with me?
Yes, sir.
Yes.
How is
Yes,
this
sir.
minimum? This is the lowest point, right? This is my lowest point. That is why it is called minimum. Now, for this lowest point, if I draw a tangent, can I use a different color? if I draw a tangent passing through only one point, okay, what will be the slope of this tangent? That will be 0. The slope of the tangent will be 0
Parallel. So
because it is
parallel.
at making an angle 180 degree. Tan of 180 will be 0. Okay. Now, so that means that for the lowest point in the curve, for minima, your slope becomes 0. So basically, the slope of equation, okay, you guys might have heard about it, that basically if you have an equation for a curve, you need to differentiate the equation which to get the slope, correct?
Yes, sir.
So slope of the equation is defined mathematically by differentiation. So for d by dx of, let's say, y, if I do the differentiation, I get my slope, correct? You don't have
Yes.
to remember this. This is just for your knowledge. You don't have to make notes also on this. Okay. So that means that if we know that slope of the curve, I mean slope can be found by differentiation, okay, and minimum value of the slope is 0. That means if I have to reduce my error, I have to differentiate my equation, that is my y actual minus y predicted. This is my error, right? So that will be effectively y actual minus beta 0 minus beta 1 x. So how is RMSE calculated? You have error, correct? This is my error, y actual minus y predicted, correct? You take square of it. I take square of it, correct? You take mean of it, and you take square root of it. You take square root of it, okay? And then to get a minimum value of beta 0, I have to differentiate it by beta 0 to get the equation for beta 0. In the same fashion, y actual minus beta 0 minus beta 1 x, you square it, you take the mean, you take the square root, you differentiate with respect to beta 1 to get equation of beta 1. So this all happens in your background. This all happens in background to get your values in solver. This is just for your knowledge. Are you guys with me?
Yes, sir.
Is it clear? Any doubts?
No, sir.
No, sir.
Sir.
Now, Now, we spoke about RMSE in our last class. Correct? Now, in today's session, let's talk about R square. Okay. Let's talk about R square error. Let's say that we are doing pricing analysis. We are doing pricing analysis of house. Okay. And none of us know how to do linear regression. Let's say that we are in the school of economics and we want to see how people price their house. Okay. What is the basic thing you would do? You have to collect the data, right? The first thing you do is to understand how people price their houses, you have to collect the data. Okay. How do you normally collect it now? Let's say you are in 1980s. How would you collect data?
From the records or something like that.
We have to go and ask people.
Yes,
Correct?
sir.
We are in 1980s. We don't have any record. We don't have any information.
Okay.
So you have to do a survey and ask people. Every house you have to go and ask कितने में बेच रहे हैं आप, कितने में बेच रहे हैं, all that. Okay. Now, let's say that you have collected this data. You have only one column, that is price. You have 50 lakhs, 35 lakhs, 45 lakhs. You have 42 lakhs, 56 lakhs, and so on. You only have one column. Okay. So now, since you only have one column, what is the best you can do from this?
Pick the minimum one.
See, basically, we want to predict the house price for tomorrow. Tomorrow, let's say some other person is selling the house. We want to predict what would be the price for that house. Okay. We only have one column of data.
So we see what is the difference or what is the change between the values and we predict.
We only have one column. What change I can see?
Like how the price has varied based on that.
The best thing you can do is you can take
Average.
average. That's all. Correct. I only have one column.
Yes, sir, yes, sir. Average.
Best thing I can do is I can go with average. Now let's say that the average of this data set is at 42 lakhs. Okay. But the peak value, that is maximum value, is at 80 lakhs and minimum value, let's say 21 lakhs. Okay. So if I plot it, I have only one axis. I have only y axis. This is my average, 42 lakhs. This is my minimum, 21 lakhs. This is my maximum, 80 lakhs. Are you with me?
Yes, sir.
Okay. So I only have my y axis. I don't have my x axis. Okay. Now, do you see that with my average, I have my spread of the data, correct? I have my spread of the data. So when we say that, how much bad are we doing in this prediction? Okay, the prediction what we are doing right now, we are doing almost as bad as this variance. You guys agree with me?
Yes, sir.
Yes.
So if the variance is too high, that means my prediction is
Bad.
bad. If the variance is low, my prediction is
Good.
decent.
Yes.
Okay, correct? Now let's bring in other factor at play. Okay, so the next factor, the easiest factor to introduce is to introduce another variable. Do you guys agree? To introduce one more
Yes.
variable here. Let's say that I bring in the square footage. Can have 800. Let's say I have 600 here. I have 650. I have 550. Again 700. Correct? And so on. Okay. Now with this data, I can do is plot a scatter plot where my square feet will come here and the price will come on y-axis, and my plot will look something like this. So each point represents one house, correct? So each point here represents the different house. Are you guys with me?
Yes, sir.
So as soon as I do this plot, I realize that as the square feet increases, my house price increases in general. Okay, that means that there is a hidden relationship between the price and square feet. Okay, and I call this relationship as linear regression, and I plot a regression line something like this. The color is not changing. I plot the regression line something like this. Correct? Passes through the middle. Now, let us take a case. Let us take a case of 700 square feet. Okay. If the house has a area of 700 square feet, somebody is selling the house at, let's say, 35 lakhs. Okay. Whereas somebody else is selling the house at 70 lakhs. Correct? Now, why is this difference? For the same square feet, I have people selling the house at 35 lakhs and I also have people selling at 70 lakhs. Correct?
Yes, sir.
Why is this difference? Our story is only hypothetical. We have no way to prove it. We have no way to prove what kind of error we are making. Correct? We are still making this much of error. We are still making this much of error in our prediction. So when we had only the house price, we made this much of error. Correct? We had this much of variance. Then when we introduced one more variable of square feet, okay, our variance reduced from this much to this much. Correct? We had variance, but variance reduced. So our basic understanding of spread, how bad we are predicting, has reduced. Correct? Are you guys with me?
Yes, sir.
Yes.
Yes, sir.
Okay. So now this variance is called my total variance. Okay. Now, with the help of my square foot, I could reduce this total variance to a smaller number. Okay. To a smaller number. Okay. And this smaller number is this error that which I'm unable to reduce is called my unexplained variance. Now, since I have my total variance here and my unexplained variance here, what will be my explained variance? My explained variance will be my total variance minus my unexplained variance. Correct? Are you guys with me? Now, let's take a ratio. Let's take a ratio. Let's divide both by total variance. Now, this ratio is nothing but my R square. This is called my R square. And basically, R square, the square is only the denotation. You don't have to take any under root here. You have to use this value directly in as is condition. Basically, this formula explains me how much of percentage variance we are able to explain. Okay. The total variance. How do you find your total variance?
By aggregating the deviations, the difference between the actual and the
You find
predicted.
the total variance from your target variable y.
Yes, sir.
Correct? You find the total variance from target variable y. How will you find your unexplained variance? That is from your error column. Correct? You find your unexplained variance from your error column. We find your total variance from your y, your total variance column. That is your target variable column. Correct? Okay. So this variance is not about a single point. So it is the variance in data itself. Have you guys made a note? Have you guys made a note of this?
Yes, sir.
Shaina, Samantha?
Yes, sir.
Let us understand this from our Excel sheet. Shall I erase? Shaina, shall I erase?
Yes, sir.
Okay. Now, we actually did train test split in our last session on the same data set. So I have my original data here. Let me just make a copy. Okay. So I have my original data here with my RMSE calculated and my slope by intercept. Okay. Now, let us find my R square. Let us find my R square error. Give me the formula for R square error. R square is my total variance minus
Unexplained
Unexplained variance.
variance.
divided by
Let me just put a
brackets.
bracket divided by my
Total variance.
okay. Now I need total variance and I need unexplained variance. Correct? So total variance is from my y, is from my y. Correct? So the formula is variance of population and select this. I have my total variance as 44. Okay. Now unexplained variance basically is from my error column is equal to relation of error. Okay. From my actual column. Okay. The total variance is from my actual column. Unexplained is from my error column, and I calculate R square. That is nothing but my total variance minus unexplained divided by my total variance. Okay. Now Is this good or bad? Is this good or bad?
It should be a maximum R square. So
R square should be as high as possible, right?
yes, sir.
Is this good or bad?
Bad.
Okay. Did you expect any good here? Are you expecting any good here? No, right? We are trying to predict the weight of a person only by the person's height, correct?
Yes, sir.
We don't know what the gender is, we don't know what the build is, we don't know if a person is vegetarian or not, we don't know anything. We only have one column, correct? So we never expected a prediction to be good. And hence now you have studied the two methods of understanding your algorithm, understanding whether the model is good or bad in regression. Are you guys with me? Any doubts?
No, sir.
No, sir.
So basically we have two things. Basically we have two things. One is my RMSE and the other one is my R square. Okay. Let me go back to the presentation. I have my RMSE and R square. Okay. If the house price is 50 plus or minus 2 lakhs, okay, this analysis can be done on using RMSE. It tells you how much up or down in all likelihood the price can go, correct? How much up or down my price can go. Okay. Whereas in R square, it tells us a similar story, okay, but in a different language. It tells you in terms of percentage, it tells us how good our prediction is, how good is our algorithm is based on a percentage. It's the same story told in two different languages. Are you guys with me?
Yes, sir.
Yes, sir.
So basically, for my R square, I have my target variable and I have my variable X. So the variance here is my total variance. Okay. And I have my regression line here and this is my unexplained variance. Okay. So basically my R square, let us call this as A and let us call this as B. Basically, my R square is nothing but my total variance minus unexplained variables divided by total variance, that is A minus B divided by A. Okay, and the value of this should be in between 0 and 1, and the thumb rule is higher the better. So the thumb rule for RMS is lesser the better, correct? So RMS is basically error, and error should be less, correct? Whereas your R square is higher the better, correct? So basically R square is percentage of error explained, and hence it should be high. Are you guys with me?
Yes, sir.
Okay. Now, let us move on to the next topic, which is nothing but linear regression in higher dimensions. Basically, we in order to have the clarity on the topic, we kept our discussion to only one variable. In the general concept of linear regression, we defined it as beta 0 plus beta 1 into x. They're having only one explanatory variable, correct? And the coefficients. These are called as coefficients. Okay. Now, let us start bringing one complexity at a time. So, quick question. How are these betas calculated? Normally, we split the data into train and test. Which data set will I use to calculate betas?
Train.
Which data set?
To calculate beta, we use the train.
We use train data set, correct?
Yeah.
Okay. And if the algorithm is good or bad, we check it using RMS or R square, and we use our test data to understand it. Okay. Now let's talk about linear regression in higher dimensions. Okay. So in machine learning, the word dimensions is actually replaced with number of variables. We often use variables than the word dimensions. Basically, we are discussing on the equations which are having higher number of variables. So we have variables something like x1, x2, x3 dash 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 up to xp, and a target variable y. And for regression, this target variable is continuous, something like your house price or ice cream sales, or even the Excel example of weight of a person, correct? So if I have to represent this equation using betas, the equation will be look like y equal to beta 0 plus beta 1 x1 plus beta 2 x2 and so on up to beta p xp, and the shorthand form is y is equal to x beta. So in general, these betas are individual weights given to these variables. Okay, to understand which, if the variable is important or not, or what is the level of importance of these variables, normally that understanding is obtained from these betas. Basically, you will understand how much that variable will affect your target variable y. Are you guys with me?
Yes, sir.
Okay. Now, we learnt about calculating the betas in Excel. We understood how beta 0 and beta 1, basically your slope and your intercept, is calculated in Excel using solver. Now in this scenario, we have more betas. We even have, instead of along with beta 0, beta 1, we also have beta 2, we also have beta 3 and so on. How are these calculated? How do we calculate these betas? Any guesses?
Using the calculus, that is differentiation.
All that runs in background. Basically, even these betas we calculate in the same fashion. Okay. Just that in the Excel, we had slope and intercept and we use 2 columns, and here we continue adding other betas and we find out these betas using solver such that my error is minimum. We still follow the same technique, correct? We still follow the same technique, just that we can no longer imagine my regression curve very easily. I can no longer imagine this because I have more number of dimensions. So this is my linear regression with only one explanatory variable. Whereas when my explanatory variable are 2, I have something like a 3D plot. We have x1 here, x2 here, and my y here. So it is as and when I increase my dimensions, I'll put a break to my imagination. I can no longer imagine how the plot will look like. Are you guys with me?
Yes, sir.
Okay. But the core concept of line passing through the points will remain the same. Okay. We still want to find out all the betas, all my betas, such that my error is minimum. Okay. Now, in a 3D plane, let's say I have my x1 here, x2 here, okay, and my y here, and let's say this is my regression line. Okay. Now in 2D, when we did y equal to beta 0 plus beta 1x, we called the plot, we called the line as my regression line, correct? A straight line passing through the points. It's a best fit line, correct? Now, as and when I increase my dimensions, I will no longer call this as a line. This will become my
Plane.
hyperplane. I will no longer stick to a single line passing through many points. It's going to be a hyperplane. It's going to look like a plane. Okay. Let me explain you with little more logic. Let's say, so my y-axis is something which is coming out of my screen. Just imagine that the y-axis is towards facing towards you. Okay, and this is my x1 and x2. Okay, and let's imagine that instead of having hyperplane, I have a regression line and it is going something like this. It's a regression line. Okay, so the core concept is for any given value of x1 and x2, okay, I should have a point corresponding on my y. Correct? So for any given value of x1 and x2, I should have my y. So for assumed value of, let's say, x1 and x2, my point will be somewhere here. Correct? Are you guys with me?
Yes, sir.
Yes, sir.
So the point will be somewhere here, and since this is a line, I will no longer interact this point with my line. For corresponding value of x1 and x2, I have a corresponding value of y which doesn't interact with the regression line. The point will be in a different plane and my line will be in a different plane. So that is the reason why I have, instead of having a line, I have my hyperplane, so that every point can interact on the plane. Every predicted points can go on the plane, and every actual point will have clear connection with your hyperplane. Okay. A quick question, that is, let's say for a 2D plot. Okay, for a 2D plot, I draw a line which is of one dimension. For my 3D plot, I draw a plane, hyperplane, which is of 2 dimension. Correct? Are you guys with me?
Yes.
In the similar manner, for p+1 dimensions, I will have a hyperplane with p dimensions. So for p+1 dimensions in space, I will have a hyperplane of p dimensions. Okay. Now, but we must remember that we plot a straight line in 2D to make it linear, correct? For a 2D plot, we draw a straight line and to make it a linear, as it is a linear regression. Okay. Now, for an increased dimensions, we are no longer plotting a line. We are referring to it as hyperplane. Okay. So the definition of hyperplane would be hyperplane is a straight entity, okay, in p dimensions. Are you guys with me? Even when you go beyond the 2D, when you go to 3D, when you go to 4D, the hyperplane will still remain plane, will still remain straight. Just that you cannot imagine that on the curve. It limits our imagination. Okay. Is it clear? Any doubts?
No, sir.
No, sir.
Let's take a break of quick 10 minutes. Okay. And let us resume at 12:15. Okay.
Okay, sir.
Is everyone back?
Yes, sir.
Yes.
Rahul, you back?
Yes, sir.
Now, before we start with assumptions, let's talk about a pitfall. Okay. We know that the equation for linear regression in higher dimension is given as something like this. Okay. Now, let us relate this with the house price. Let's say we have age of the house in years. We have the square feet area and we have the price in lakhs. Okay. So the price could be somewhere in 50, 45, 30, so and so. Square foot would be your 1000, 1500, 900, so and so. The age would be something like 1 year, 3 years, 2.5 years, and so and so. So if I have to write this in equation form, it's going to be price equal to beta 0 plus beta 1 times age plus beta 2 times the square feet. Okay. Now, if you see the tensors here, the price is in tens, your 50s, 60s, 30s, correct? Okay. Whereas your age is in units. You have 1 year, 3 year, 2.5 year, correct? And the square feet is in hundreds. You have 900, 800, 1000. Okay. So all you can see that the units are not balanced. You guys agree with me?
Yes, sir.
Okay. Now, what should I multiply with this beta to balance this unit? What should I multiply with these betas to balance this unit? I want the price to be in tens. How should I balance this equation? Since the age is in units, if I have to bring it to tens, I have to multiply by
10.
10, correct? What about square feet?
You need to divide by 10.
I need to divide by
it
10.
10. Yeah.
Correct? Okay. Now, let us take hypothetical examples. Let's take beta 2 as 0.2. Okay. And beta 1 as 40. Okay. I am maintaining same decimal places as required here. Okay. Now, can I conclude that my age of the house is 400 times more important than square feet? based on the weights I see here, correct? Can I conclude my age of the house, basically my beta 1, is 400 times more important than my square feet? I can conclude from my data, right?
Yeah.
But we should not do it. It does not make sense to give more weightage to age than square feet. So our conclusion will go haywire. Okay. So before we run machine learning, let's do a thing. Okay. Let's make sure that all the variables are in the same scale so that we can properly compare the weights. You guys agree with me? So before we do machine learning, we do the scaling of variables so that we can properly compare the betas, which variable has more weightage. Correct? Now, this activity is called my scaling. Okay. This activity is called scaling. Okay. Basically, in scaling, what I do is I multiply and divide my each column. Okay. Such that all the columns okay, I multiply and divide all the columns such that all the columns in the sense only my explanatory variables. I did not touch my target variable. Okay. I multiply and divide such that all will be in same units. The units in the sense not your millimeter, centimeter, the same tensors. Are you guys with me?
Yes, sir.
So
Yes,
once
sir.
I do that, I will be able to compare my variables, correct? Do you see the requirement of doing it? The requirement is once I run my test data and get all the betas, I can see the weightage of individual variables. Which variable has more importance based on my betas, the weightages received from my algorithm. But in order to do that, all my variables should be in the same scale. Okay. In Python, there is an automatic way to do this activity. Okay. And it is called standard scaling or standardization. The process is called standard scaling or standardization. Okay. And this standard scaling or standardization is applicable only for my explanatory variables. Only for my explanatory variables. So what it basically does is, I have my x1, x2, x3 and so on. Let's say x4. It will replace my values by x minus mu by sigma. What is mu? What is mu?
Average.
This is my mean. What is the sigma?
Standard deviation.
Standard deviation. You guys have seen this equation somewhere else.
Normal. Standard normal.
Standard normal, that is your
Center limit theorem also.
Z score. The formula of Z score. Basically, you're replacing these values with your Z score values. Correct? Now, is this the only way of scaling? The answer is no. There are more ways to scale your data set, but for today's understanding, let us follow the simplest form. Okay. Okay. Let us go back to our Excel. Let us go back to our Excel. And okay. Now, which is y in this? Which is my explanatory variable? Height is my explanatory variable, correct?
Yes, sir.
Let me copy it and paste it here. Okay. Now, in order to do the scaling, I need to find my mean and standard deviation, correct? Average of and I have my mean and standard deviation. Okay. Now, give me the formula. Basically, the formula is what is the formula? X minus.
Mean.
I can insert the symbol. X minus mu, correct? Divided
Yes,
by
sir. Sigma.
sigma. Do we have sigma here?
Greek, sir.
I went to acrylic. They have sigma in different notation. By I'll just put standard deviation. Okay. Now equal to what is my x? Shaina, which column is my x?
The height.
Height minus, where is my mean? Mean is 67,
The
correct?
67.
I'll use function f4 to freeze my cell, divided by my standard
Standard.
deviation and function f4. Okay. And I do it for my complete data set. Okay. Now, we understood that for a standard normal deviation, my mean is 0 and standard deviation is 1. This is something like 0.000015 zeros, correct? Followed by 92 is almost equal to 0 only. Standard deviation is 1. Are you guys with me?
Yes.
Okay. Quick question. Do I really need to do scaling when I only have one variable, one explanatory variable? I only have one variable here. Should I need to do scaling? The answer is no. I only have one variable, right? I only have one variable. Is it clear?
Yes.
Yes, sir.
So your standardized data will always have your mean as 0 and standard deviation as 1. So no matter what your data set is, you will always having this value. Okay. Now, before we start with assumptions, now we are clear with linear regressions, correct? And what we understand that before we apply linear regression, we must do train test split, correct? Once we do train test split, we must do scaling or standardization. Okay, and only then carry out your linear regression to find your hyperplane such that my error is minimum or R square is maximum, correct? Are you guys with me?
Yes, sir.
Yes.
Now, just missed one point. Okay, now tell me what is wrong with this second graph. These are my errors. Okay, what is wrong in this particular graph? What is the formula for error?
Actual minus predicted.
Y actual minus Y
Y
predicted. Okay, so any guesses? What is the issue with this particular graph? What is the problem you see it here?
I guess here it is predicted minus actual.
No. See, basically when I say Y actual minus Y predicted, I am measuring the points with respect to my Y axis, correct? So I need to find the points which is parallel to Y axis. This distance, the distance should be parallel to Y axis, correct? And not perpendicular to the hyperplane. Correct. Error is given by y actual minus y predicted, right? You have to measure it with respect to y axis, not with respect to the hyperplane. Clear? Now, coming to the assumptions. Okay, now okay, so first time when I started to work, my house was in Kerpura. Okay, and office was in Hoskote. Okay, basically in Bangalore. And I had to travel all the way morning and evening to reach office and back. What I did was I recorded the time taken to travel. Okay, and it came something like this. I have 20 minutes, 25 minutes, 35 minutes, 24 minutes, 21, 30, 21, 22, 24, 20, 18, 17, 22, 26, 24, 27, 21, 31, and so on. Okay. And with this data, I plotted a distribution. I plotted a normal distribution and I got mu equal to, since I have a lot of 20s, let's say I got my mean as 21.5 minutes. This means on an average, I take 21.5 minutes to reach office. Are you with me? Okay. And if this is 21.5, 22, 23, and so on, 17, 18, 19. Okay. This is how my normal distribution looks like. Now, this is my standard deviation, correct? Like how much variance I can explain. If the standard deviation is small, that means I'll have very less traffic and I travel often and sooner. If the standard deviation is more, that means oftentimes I end up getting more traffic, correct? That is unreliable traffic condition. So since I said that on an average, I take 21.5 minutes to travel, does that mean that if I have a meeting or with CEO, okay, in morning, should I start 21.5 minutes early? This 21.5 explains how far am I located from the office. So if I have a meeting with CEO at 9 o'clock in the morning, should I meet somewhere at 8:42 or 8:41 minutes and 30 seconds? What is your opinion? Any answers? I had to go early, right?
Yes, sir.
I had to travel much early. So it will be mu plus something into my standard deviation, correct? That will be my time taken. So if I go with one standard deviation, how soon can I reach?
21.5 plus the variance, standard deviation.
Correct. If I go with that, with what confidence interval I can tell that I will reach office on time? We had this discussion in EDA, right?
Yes, sir.
That is,
1 sigma limit
one
is
standard deviation will be
68.
how much? 68%, right?
Yeah.
So I can say 68% confidence that I will reach on time. Correct. If I go 2 standard deviation,
95%.
95%, right? If I go 3 standard deviation,
99%.
99%. Okay. Now I want to be 100% sure that I want to reach on time. What should be my value here? The best answer is not to leave from office the previous night. Even if I take 6 sigma here, I will end up with 99.9999% and never 100%. Okay, so this is not calculating beta in your linear regression. This is just your simple statistics. Is this clear?
Yes, sir.
So hope with this small discussion, you understand that you can apply statistics in your day-to-day life also, and you don't have to learn data science for it. So with this discussion, we were able to revise on normal distribution, correct? How the bell-shaped curve is, what is the confidence interval for the points, correct? Okay. Now, with this, let us come to the first assumption. Basically, this is could be your interview questions when they ask on linear regression, like tell me the assumptions for linear regression. Basically, we have 3+1 assumptions. Okay, I'll only cover first one assumption today, and then other assumptions we can, 3+2. The reason why I'm saying 3+2 is because when you try these 3 assumptions, if your data set proves to be true for these 3 assumptions, then automatically it satisfies these 2. Okay, so basically you need to focus on these 3. And the first assumption is that your target variable must be, I'll take the black screen. The first assumption is that the target variable must be normally distributed. Are you guys with me?
Yes, sir.
Basically your x and y, which is your target variable? Which is your target variable? Y is your target variable, right? Target variable or dependent variable, whereas X are your explanatory variables or independent variable. So what the first assumption says is that your target variable must be normally distributed. Okay, now how do I check it? How do I check it in Python? How do I check this? Very simple answer. I plot it, correct?
Yes, sir.
I plot it, right?
Graph.
I can use KDE plot. Correct? What is the second method? The hint is here only.
Calculate the mean variance or standardize it.
You are very close.
Median.
Shaina said it right.
Okay.
Mean equal to median.
Median equal to mode. Mode is not. Okay. Mean equal.
Mean equal to median. Correct? It should be, I'm not saying it should be absolutely equal, it should be roughly equal. It should be roughly equal. Okay. Now, where do I check it? Where can I check this? Let's say I'm doing this in EDA. I'm carrying out EDA. In which stage I can check this? Mean equal to mode or mean equal to median?
Box plot.
Dot describe.
Yes, sir. We get all the information. Yeah.
Dot describe, I'll get information, right? You can
Yes.
also check using dot skew. You can understand on the skewness of the plot. Just like dot describe, you use dot skew. If the skew is very small, then that is fine. If the skew is large, then you are in trouble. Okay, now let's say your target variable is not normally distributed. What should I do? How do I correct it?
By standardizing it.
Standardizing won't work. You are standardizing your explanatory variables, whereas your target variable, you're not touching it, correct? One is you take log of target variable, or you take square root of your target variable. One is you take log of your target variable, or you take square root of your target variable. So what happens in either log or square root is that, let's say I take log. This is my log x and this is my x. So what happens is the graph will look something like this. For small value of x, okay, the small value of x, it increases quite fast. And for larger value of x, it tends to remain the same. It doesn't increase much. This is for log. And whereas for square root, it looks something like this. It looks the same. So the variable will become normal after taking the log, and it is called log normal. Again, you don't have to remember these nomenclatures, just for your understanding. Have you guys made note of this?
Yes, sir.
Samantha, Shaina?
Yes.
Yes, sir.
No. So the assumption, the first variable, that is the first assumption, is nothing but the target variable should be normally distributed. So this is how you check it, is using your KDE plot. Okay, and if your target variable is not normal, what happens is you take a log transformation to convert it to a normal. You see that here it's 5, 0, 5, 10, 15, whereas it is all the values which were here are being pushed now. You have 0.1, 1 and 10. So the plot looks normal. You will have more clarity when we start working on the Python code. Are you guys with me?
Yes.
Yes, sir.
So this is where I stop our session. And the next class, we will continue with the balance assumptions and start with our Python exercise. You guys have any doubts?
No, sir.
Shaina, Samantha, any doubts?
No, sir.
No, sir.
Okay. In case you don't have any doubts, you can drop off. If you have any doubts, you can stay back.
Thank you, sir.
Thank you, Shaina.
Thank you, sir.
Thank you,
Thank you,
sir.
Rahul. Thank you,
Have a great
Samantha.
day. Bye.
You too. Bye-bye.